Up to this point, we've learned Go in focus pieces: structs, interfaces, errors, tests, goroutines, channels, context, and project layout. Now we put those pieces under pressure in one real tool: a concurrent web scraper. The goal is not just to fetch web pages. The goal is to design a small Go application that has clear boundaries, can be tested without the network, and has room for concurrency without turning into a mess. The Capstone project is a command line tool called Scraper. You give it one or more URLs. It fetches those pages, extracts useful information, and writes structured results. In the final version, each result will include the original URL, the page title, links found on the page, any error that happened, and the time the page was fetched. This project intentionally touches almost everything we've covered in the course. Modules give us the project structure. Structs give us the result data model. Interfaces give us testable boundaries. HTTP and file I/O connect us to the outside world. Context, error group, channels, and a semaphore let us run multiple requests while still keeping control over cancellation and resource usage. This episode is the architecture episode. We are not going to build the entire scraper yet. We are going to decide where the code lives, which packages own which responsibilities, and which interfaces keep the pieces independent. Before we create files, start with the path one URL takes through the program. The CLI parses arguments and turns them into a list of URLs. The scraper package coordinates the work. For each URL, it builds an HTTP request with a context, fetches the page, sends the HTML to an extractor, then wraps the output in a result value. At the end, the CLI saves those results as JSON. That flow tells us where the boundaries should be. Parsing command line arguments does not belong in the extractor. HTML parsing does not belong in the CLI. HTTP orchestration does not belong in the result type. If each package owns one job, we can test each piece separately. The layout follows a common Go shape. CMD/scraper holds the executable entry point. That package should be thin. Parse input, wire dependencies, call the application, and handle final output. Internal/scraper holds the orchestration logic. It is internal because outside projects should not import our implementation details. Internal/extractor holds HTML extraction logic. That is separate from the scraper because extraction is a different concern from fetching. Package/result holds the public result type. This is the data shape other packages might reasonably consume. URL, title, links, error, fetch timestamp. Keeping that type stable gives the rest of the application a shared vocabulary. Think of this project as 4 cooperating parts. The CLI is responsible for user input and output. The scraper is responsible for coordination. The extractor is responsible for turning HTML into data. The result package is responsible for the data contract. The important design habit is that dependencies point inward toward smaller responsibilities. The CLI can depend on the scraper. The scraper can depend on an extractor interface and a result type. But the extractor should not know about command line flags, and the result package should not know about HTTP. This keeps the project flexible as it grows. The first concrete type is result. It is intentionally boring, and that is a compliment. It has the URL that was fetched, the title, a slice of links, an optional error string, and a timestamp. The JSON tags matter because this type will eventually be saved to disk. JSON error, omit empty, means successful results do not include an empty error field. The timestamp uses time, which marshals cleanly to JSON and gives us precise, sortable output. This is also a good example of where not to over-design. A data type does not need a pile of methods just to look important. Start with the data contract, then add behavior only when the rest of the project asks for it. The extractor package defines an interface with 2 operations: extract a title from HTML and extract links from HTML. The first implementation uses regular expressions because it is small and easy to demonstrate. In a production-grade scraper, you might replace that with an HTML parser from golang.org/x/net/html. The point is that the scraper does not care which implementation it receives. It only cares about the interface that lets tests provide a fake extractor. It also lets us improve the extraction implementation later without rewriting the fetching and concurrency code. Notice the slice and map pattern in link extraction. We presize the slice based on the number of matches, and we use a map to deduplicate links. That combines two earlier lessons: efficient slices and maps as sets. The scraper package is where the application starts to feel real. It owns a config, an HTTP client dependency, and an extractor dependency. The constructor receives those dependencies explicitly. That means a real CLI can pass HTTP.default client, while tests can pass a fake client. In this episode's demo, the scraper can build a request, explain its concurrency plan, and build a result from sample HTML. That may seem modest, but it proves the architecture compiles. More importantly, it proves the packages are allowed to depend on each other in the direction we intended. Episode 27 is where this package grows the real concurrent fetch loop. Today, the job is to make sure the foundation is clean enough to support that loop. The concurrency design has 4 pieces. First, context controls cancellation and timeouts. Every HTTP request should be tied to a context so slow work can be stopped. Second, AirGroup coordinates goroutines and gives us one place to wait for them. Third, a channel gives goroutines a safe way to send results back to one collector. Fourth, a semaphore limits how many requests run at once. That last piece matters. Concurrent does not mean start 1,000 requests and hope. A scraper should be polite to remote servers and gentle on your own machine. Limiting concurrency is part of correctness, not just performance tuning. Error handling has 2 layers in this project. Some errors belong in the returned go error path. Configuration is invalid. A file cannot be written. The whole operation is canceled. Other errors belong inside individual results. One URL failed, but the rest of the batch can still succeed. That distinction is important. If one page returns a bad status code, we may still want JSON output for every other URL. But if the user cancels the command or the output file cannot be written, the command itself should fail. Designing that policy up front keeps the implementation from making random choices later. Now we run the skeleton. The command prints the package layout, wires the extractor into the scraper, builds a request with a user agent, extracts data from sample HTML, and prints the resulting JSON. There is no live network request yet. That is intentional. We want the first demo to prove the shape of the application before we add concurrency. Then we run go test /. The tests check that the extractor gets a title and deduplicated links, and that the scraper applies configuration to requests and produces the expected result shape. This gives us a clean checkpoint. If episode 27 breaks something, we have tests around the boundaries we designed today. In this episode, we turned the Capstone idea into an application architecture. The CLI owns user interaction. The scraper owns orchestration. The extractor owns HTML parsing. The result package owns the output data contract. We also planned the concurrency model: context for cancellation, AirGroup for coordination, channels for collecting results, and a semaphore to limit parallel work. Next episode, we implement the real core: concurrent fetching, extraction, result collection, and timeout behavior. This course is based on the complete guide to Go programming, available on Apple Books and Amazon. Find it at pixelstech.net/book. See you in episode 27.